Hello, everyone. Welcome to CAC webinar. So today we have invited Mr. Jeffrey Faden, the President and the CEO of McMod Analytical, to share with us the latest LC column technique, monodisperse fully porous particles. So this is the first part of the webinar series. In this part, its main focus is on the fundamentals of how to significantly improve the column efficiency. The second part of the webinar, which is scheduled on February 5th, will talk about the applications of the new column, especially to the oligonucleotide separation. So first of all, I want to have a very brief introduction of CACA and its activities. So CACA builds a community for separation scientists, provide support on career development and networking, sponsor webinars, symposium and conference, award excellent young scientists and students. So last week, we just announced the 2025 winners for the Excellent Student Award and the Young Investigator Award. These awards will be presented to the winners at PeterCon CACA dinner event. CACA's main activities include networking and dinner event at PeterCon every year, at HPLC conference every other year. We also organize technical session at EAS meeting and other conferences. So if you want to know more about CACA, you could visit us at our website or join social media group at LinkedIn or WeChat. Here is the list of our recent webinars. We also archive our past webinars and the recordings are available as well. These webinars covered wider topics in the field of separation science. So here, I also want to say thank you again to our sponsors. So thanks for their strong support to make all this wonderful thing happen. CACA webinar team, including myself, I'm Dr. Yi He at Georgia College, the City University of New York, Dr. Fengjian Shi at AstraZeneca, and Dr. Howard Guo at Sanofi, and Dr. Tao Chen at Genentech. So our speaker today, Mr. Jeffrey Faden, is the president and CEO of McMod Analytical. He received his Bachelor of Science in Chemistry from Pennsylvania State University in 2003, and his MBA from Temple University in 2014. He has served as a trusted chromatography partner for the life science industry for over 15 years. He has experience working with major pharmaceutical, biopharmaceutical, industrial chemical, and environmental companies to improve their workflow and provide innovative solutions to their challenging chromatography-related problems. He has been acknowledged on several publications and posters and has frequently been counted on to provide industry-leading technical support, presentations at conferences, meetings, and on-site at customer facilities. So now, let's invite Mr. Faden. So now I'm going to change the screen to Mr. Faden's screen, and it will take a few seconds.
Hello. Thank you for that tremendous introduction. Where McMod Analytical is proud to be a sponsor of the CACA group. We've been a long-term sponsor, and also I think we've sponsored some of the awards as well over the years. So as a long-term partner, we thought it'd be interesting to talk about our new particle technology that is revolutionizing LC. So this is part one. The title of the talk is New LC Particle Technology, Monodisperse Fully Porous Particles. Let me move to the next screen. There we go, a little bit of a lag. Okay, so basically, I wanted to talk about the evolution of UHPLC and HPLC particles. When you think about HPLC, the particle itself, there's different things that have uh, basically evolved since the advent of the first, porous particle. The particle morphology has changed over the years. They originally were irregular shaped, then they became a follicular glass bead, and then a fully porous spherical particle. The particle size has dramatically decreased. So some of the initial particles were 100 micron, and then 50, and then 10 and 5. And as the instrumentation got better, we could also, build better tools for the instrumentation. And now you'll see pretty commonly 1.7 micron particles. Over time, they found that the metals content in the silica would affect the peak shape adversely or beneficially in some cases. And the more they were able to improve and reduce the metals content, the more they could control batch-to-batch reproducibility. So initial purity was type A, and now they've been on to type B silicas. And the big innovation here that we're talking about is really the particle size distribution. What we're showing is a monodisperse particle, and so we're using a way to characterize that as a D90/10 parameter that has dropped significantly. So what you see here is a Coulter counter. In the middle, you have the branded product called Evosphere. And on the left, you have a commercially fully porous particle, very popular from column manufacturer A, and one from column manufacturer for B. And what you can see is the particle size distribution is much narrower, and that inherently gives some benefits. So how do you characterize particle size distribution? Well, you take the distribution of particles at the 90th percentile, and you take the distribution of particles at the 10th percentile. And when you look at the initial, everyday commercially porous silica that you're using in your lab currently, if you had done that analysis, you get about a factor of 1.6 as your D90/10. What we've been able to do is minimize that D90/10 to about 1.1. So when you actually take a look at the particles, the fully porous particles, which we would characterize as polydisperse, your normal HPLC column that you have in your lab today probably looks, if I would unload the silica from the column, you would see a range of particle sizes. But what you were able to do now is really narrow that particle size distribution, and you can easily see that on the monodisperse particles, they're all the same size. So why is that important? Why should we care? When you look at the resolution equation, you have three main parameters that affect resolution. You have your efficiency term, your retention term, and your selectivity term. What we're going to be talking about is how the distribution first affects the efficiency term. And so how do you calculate the efficiency of an analytical column? Well, you would take the length of the column divided by what we call a height equivalent to a theoretical plate. That terminology came from dissolution, actually, where they actually had physical plates in the big dissolution column. Sorry, distillation, not dissolution, distillation column. The way you calculate height equivalent to a theoretical plate is simplified Van Deemter equation. So you have your A term, your B term, and your C term. So H is equal to your HETP from the previous graphic. So the A term is your eddy diffusion or the multipath effect, or the way the analytes travel through the analytical column through the interstitial. The B term is your longitudinal diffusion, or how the mobile phase also sort of diffuses as it passes through the column. And then your C term is this term called resistance to mass transfer, how much resistance the analytes get going in and out of the pores of the packing material. When I talk about this, I like to actually show the expanded terminology because it at least gives a better sense of what is being acted on in the chromatographic technique. So when you look at the A, B, and C term, this is really what the math is behind it. So just looking at the C term all the way to the right, when Van Dienter wrote this equation, he had to account for gases and liquids. So the C term is broken up into a gas diffusion, so that term immediately goes to 0. So then you look at, you sort of minimize the C term because small molecules pretty much diffuse really fast in and out of the pores. Now, as the analytes get bigger, that resistance to mass transfer term becomes much more of a concern. When you look at the B term, that term also gets minimized because your gases will diffuse very, very widely in a chromatographic system, but in a liquid chromatography system, the other effects of the liquid, like your hydrogen bonding and van der Waals forces, causes the liquid to sort of stay together. So the B term tends to be minimized as well. So what we really see is this A term, and then the A term can get simplified to 2 lambda dP, which lambda is the packing factor. And so if the dP stays consistent, because dP is your particle size, and 2. So if we can minimize that packing factor, we can then really reduce that height equivalent to a theoretical plate, and that was in the denominator of our efficiency term. So then our efficiencies should go up. So visually, what does that look like? The math is nice to look at, but visually you can see that the way we're minimizing that packing factor is all the particles are the same size, so it's packing a very uniform packed bed. Thus, when a particle or when an analyte goes in and out of a pore, it doesn't have to take an immediate right turn necessarily. And so the dispersion that happens in the band is much less. And so what do you get? You get higher efficiency, which is exciting. It's really interesting because you weren't necessarily able to get that without dropping the particle size down to 1.7. So now we're bringing those types of UHPLC efficiencies, but at bigger particle sizes, and we've made smaller particle sizes available as well. So, the take-home message is, in a 3 micron, we're getting higher plates. And in this example, this is on the same system with 2 different columns. One's a very common commercially grade column, and this is our Evosphere C12 versus a C18, and you're getting about 60% higher plates. You might say, okay, well, that sort of sounds like an innovation from 2005. And so you'd say, oh, there was this technology in 2005 that came out called core shell. Core shell was really bringing the initial advent was because you had all these UHPLC columns and UHPLC instruments come to the market, but you had a lot of legacy HPLC systems. So if I could bring a high efficiency particle onto a legacy HPLC system, I would have a pretty exciting product. And so core shell sort of revolutionized the industry over the last 15 years. But it has its drawbacks because in a core shell particle, it can't mimic the loading capacity of a fully porous particle. And what they don't tell you about core shell, or what I'm telling you, is that core shell particles are also monodisperse. And the optimized pack bed that they pack is very similar to the difference of the Evosphere that we're packing here. So the benefit really is you are increasing the loading capacity while mimicking core shell benefits. And so what does that allow you to do? Well, now you can pack semi-prep and prep columns. You get a little bit more retention, similar to fully porous. So there's going to be situations where the surface area really comes into handy, because you have a surface area of 350 meters squared per gram, which is almost 3 times the surface area of the core shell material. You can get more interaction with the stationary phase. So we're showing higher efficiency, more retention, and scalability to prep. So people say, oh, well, I really want to see a Van Deemter so you can prove this out. Well, here's a Van Deemter of the monodisperse particle in the similar particle size, 3 micron versus 2.7 of a 2.6 of a core shell material. And you can see at higher linear velocities, the Van Deemter pretty much flattens. So you can run faster and not lose plates. And then secondarily, when what I was talking about previously is you have this loading benefit. So a lot of times in drug product, drug substance, you're seeing very small impurities that are next to this big, major API. And in order to see it, you got to keep loading and loading more and more onto the analytical column. Well, at a certain point, at 1 meg, 2 megs, 3 megs per mil, you start to lose the efficiency of the initial peak just because you don't have the loading capacity, that surface area that becomes such a benefit. Whereas here, the surface area stays consistent. You have that accessible surface area to load more and more into those pores. And so that really doesn't affect your efficiency, and you get a little bit more retention. Retention can be a key parameter, especially when talking about how to retain polar compounds in reverse phase, which we'll talk about later. So, I like to show the resolution equation again because selectivity really ends up being the key to resolution. So if you can build a unique particle structure that is innovative and bleeding edge and is going to be quote unquote, changing the separations significantly from a efficiency perspective, you still really get the square root of that as it impacts resolution. So what else will impact resolution? It's your selectivity. Selectivity, as you can see here, is almost linear to resolution. So the way you really change your selectivity is to bond different phase chemistries onto the silica bead. And here we're able to offer 8 different phase chemistries right out of the box on monodisperse particles. And each one has some unique advantages, and I really like them. That there's some that are unique only to Evosphere as a brand, and I have my favorite one I'll talk to you about later. So one where, this C12 is interesting because you can actually bond more C12 onto a silica surface in some cases than the C18. And so that coverage gives you some unique benefits, especially to minimize the salinol impact. So what we've seen some applications, one, this is expands the pH of the material because you're not able to attack that salinol bond at mid to high pH. But two, we've seen some really nice separations with peptides with the C12. So also as peptides, you need to do isolation purification, and we can scale this to prep. But it basically gives you hydrophobicity on the C12. My favorite chemistry here is this diphenyl. It's actually based on a diphenyl hexyl, so it's a stabilized diphenyl. Popular chemistry that a lot of people use is a biphenyl. This is a diphenyl that gives similar selectivity but different interaction because the phenyl character is not lining up straight, it's lining in sort of like a landing strip. So it does give some unique selectivity there, and so we've seen it as a really good alternate to selectivity for C18 and biphenyl. And the other benefit is it doesn't bleed because of that stabilized phase. So we're in a good spot there. So the next one is the C18 PFP. So here is interesting because you get hydrophobicity and regioisomer selectivity. So what we have here, you get some steric selectivity, polarity, dipole charge. And so I'll talk about how we're using the C18 PFP in the metabolomics application later on. We offer the C18AR. This is what we would classify as our de facto L1 column. So, if you want to replace your C18 This one's a good one to look at. Extra steric selectivity for the are bonded to the surface. Really interesting column is the aqua, sort of misnomered here because it's really polar retentive. And what we've seen is, especially for nitrosamines, is an excellent retention and able to separate the two key parameters of the nitrosamines in LCUV, so you don't have to use LCMS. So for like batch release in QC, this column has been really exciting. It has excellent stability like all the other columns, and obviously named Aqua, it can be run at 100% aqueous. RPAMID is a great tool for the toolbox because it gives you great peak shape for bases at low pH. And then phenylhexyl, because you have a different selectivity that people like. Then PFP also can be run in Hillock mode, and you have some shape selectivity there. We know that the pharmaceutical market is not going to be interested in these columns unless they are batch-to-batch reproducible. The cool thing about monodisperse particles is the way it's made, being that you have to control all these parameters very, very tightly. It's not made like a chemical sifter where we take the big particles out and the small particles. It's actually made in a synthesized step. It inherently has really excellent batch-to-batch reproducibility because all the particles are the same size. And then this just shows the retention times are scalable as you change the particle size, which is a nice benefit. So if you're developing a method in the US on a 1.7 and you say, hey, I got to translate that method to China, we can do that on a 3 micron or 5 micron, and we can mimic a lot of the same separation capacity. So we partnered with a collaborator at the University of Florida, Dr. Tim Garrett, and he's used the C18PFP for a while now for untargeted metabolomics methods. So here's the total ion chromatogram, and we focus in on the arrows that are sort of the unique benefits of the column. So being able to retain 5-aminopentanoic acid and valine in just formic acid is pretty exciting because you're really leveraging not only the higher surface area of the monodisperse particle, but also the phase chemistry. And we're getting baseline separation here. This is in the 100% aqueous portion of the gradient. This one tends to be the crowd pleaser, is separating isoleucine and leucine from each other. We've actually further done more where we've separated allo-isoleucine with a 1.7 micron as well. But this is a really difficult separation because it's one methyl position switch. Then we have really good peak shape for acetyl-carnitine, for a base that's pretty tough to do. And then just showing tyrosine and phenylalanine is separated, really just one hydroxyl group different between the two analytes. And then this is another benefit in an untargeted where they want to understand the lipid character and try to get the metabolites at the same time. So here you're able to get the SN1 and SN2 lysophospholipid isomers separated, which can be beneficial because this could lead to other disease states that they like to know about or like to at least get a hint at what the doctors can treat. And then with that, I just wanted to talk about how we're further expanding the product portfolio. So there's been a lot of interest in coated hardwares because analytes can chelate, or really sticky analytes. What we'll be talking about next time is a separation where we're using this coated hardware with the C18AR in a collaboration with a Polish university, where the frit is coated, the innards of the column is coated, and so it doesn't give any loss in signal. You don't have to, because you could get away from using the coated hardware if you did like an overload injection, but it actually the hardware is actually worth it in the price of the column because the analytes are so expensive to run. So what the cool thing is that we're offering is not only are we offering coated hardware in analytical sizes, but we're offering you coated hardware in the monodisperse particles in prep sizes, which is exciting because if you wanted, we're able to separate one base pair of the oligonucleotide separation, which I'll show next time. And then you can scale that application right up to prep. So we call Evosphere Max. That's for our small molecule line, which I was talking about previously. We've expanded the Evosphere particle size, or sorry, pore size from 100 angstrom to 300 angstrom with 4 chemistries as well. So this is exciting because peptides and protein separations that can benefit from higher efficiencies and more retention, are pretty much unlocked here. We've had one recently where we've seen excellent QC results on a a C4 Bio 300 that's been really good, really exciting. But again, as you use these peptides and proteins and monoclonal antibodies and bispecifics and any of these or plasma for that matter, the coated hardware can just, first injection, once you've equilibrated the column, you're ready to go versus having to get to some steady state based on some interaction with the metal surface. So we're offering the Evosphere Bio and in the Max hardware, and we call that Evosphere Bio Max. And so in conclusion, monodisperse fully porous particle technology, it eliminates the weakness and combines the strengths of traditional superficially porous and fully porous particles. It offers efficiency similar to superficially porous particles without the loading limitations, and it allows you to scale to semi-prep and preparative sizes for your medicinal chemistry folks and your isolation purification folks, which provide significant method development advantages. So not only that, but the introduction of the monodisperse fully porous particle in the wide pore, as well as max coated hardware, extends just an unlimited application breadth. And we're just really excited to see where this technology goes over the next 10 to 15 years. So with that, what I'd like to say is please stay tuned to part 2 of the webinar series in our partnership with CACA. We're going to be leveraging this monodisperse fully porous particle platform for really deep dive into oligonucleotide separations. And then we're also going to be talking about how we're leveraging the platform for new invitation in different modes of chromatography like size exclusion, ion exchange, and HIC. So with that, I'd like to turn it back over to E and take any questions.
Okay, thank you, Jeff, very much. Okay, yeah, so our next part is a Q&A session. So Jeff will be here to answer your questions. So then, if you have any questions, then you can feel free to type in the chat box, or we also have the we also have the box for you for the questions. Okay. Okay, yeah, so Jeff, so now I have a question. So how is the batch-to-batch performance of the monodisperse particle technology?
Yeah, it's interesting because the way we make it is, so you have to make it in smaller batches to control the monodispersity, but that allows you to really control the manufacturing process. And so inherently, because all the particles are the same size, you almost get a step up in batch-to-batch reproducibility. So we have 3 batches available pretty much at all times, and we're seeing really robust results batch-to-batch. So we've actually seen a significant benefit from the monodispersity when it comes to batch-to-batch reproducibility.
Okay, yeah, it's wonderful. Yeah, actually, it's a very exciting news about this high reproducibility. And yeah, so that I have a question here. Is there any specific treatment that needed to be done to the columns to utilize them?
No, so that it's based on silica. So you would treat it like in reverse phase, standard, you would do 20 column volumes to get it up and running, and then store it in, your normal storage solvents, depending on what mobile phase buffers you use. It can be used in acetonitrile, methanol. We've seen, any of the silica-based mobile phase chemistries that are you usually use with silica. So there's no on the monodisperse particle platform at all.
Okay, yeah, very good. Yeah, I saw hands on from our audience. So then I just unmute and then they can ask directly.
Sure.
Okay. Yeah, Perry, I saw your hands are up. So would you please unmute yourself and ask the questions?
Hi guys, can you hear me?
Yes, yeah, we can hear you well.
Okay, Jeff, you did a good job. Question for you. For your new column, so how seriously you treat the column with the pH? So how low you can go or how high you can go? What's the pH range for your new column?
So the C12 phase chemistry, we actually do have pH data where we did lifetime studies, and we were able to use it over 10,000 column volumes at pH 11 for the C12, and so that was giving some exciting advent for oligonucleotides because they tend to be run at
High
mid
pH.
pH and high
Yeah.
temperature. But the other phase chemistries are pretty much pH 2 to 8. So C18, all the rest of them outside of the C12. And I think the C12 is because just the ligand density coverage that you're able to get on the silica is so dense that you're not really affecting the silica dissolution.
Got you. So earlier you just mentioned the temperature. So how high temperature you can tolerate for your column?
I mean, it's chromatography is a compromise. You can melt it if you want it, but you're not going to get the lifetime out of it that you get. So we recommend, at low pH for the longest lifetime, 60 degrees C at the highest, and at mid to high pH, 40 degrees C.
Got you. Thank you.
Yeah, you're welcome.
Yeah,
See you at
thank
the
you very
Beacon?
much.
Are you going to the Beacon?
Yes, I'll be at PitCon.
Okay, see you there.
All right, great. Thanks, Barry.
Sure.
Okay, thank you. Yeah. So yeah, if you have any questions, you are also welcome to raise your hand and then unmute yourself to ask. Okay, so now I have received another questions. So what observations have you noticed about the new technology that were unexpected?
Yeah, so the surface area is actually pretty high for a silica-based particle. I think some of the more common like the hybrid technologies can be in the lower or the higher 100 angstrom or meter square per gram surface area, whereas this is 350 meters square per gram. So we're seeing with that surface area as a secondary benefit is more retention in general. So polar compounds, I showed the one where we're able to retain isoleucine and leucine. Those log Ps were around -2. So that's pretty good in reverse phase. So it seems that as we're learning more and more about this high surface area, that if we were able to continue to do some bonded phase innovation, that we might be able to really bring in some of those more polar compounds in reverse phase and not have to do, let's say, ion pair or derivatization or have to move to Hillock. So that was sort of unexpected, where just really across the board, we're starting to see more retention than what we would normally expect on a standard silica-based reverse phase column. And then with the retention, the surface area, you get the loading capacity benefit as well. So then it becomes a really interesting thing for the prep folks in medicinal chemistry or isolation purification groups.
Okay, yeah, great. Yeah, so then what are you most excited for with this new technology?
You know, I think there's for, you know, folks to get their hands on it and see what it can do. You know, I'm really, every day we get another person that's tried it that, you know, gives us really exciting feedback. You know, able to, that a little bit of extra efficiency, you know, 60%, you know, you get the square root of that, that's 20 or 30% bump in resolution. You know, so, you know, pulling that API apart, solving those problems for customers is really what MacMod's all about. And I think that, you know, this new technology is just going to continue to allow us to help solve our customers' problems. So that's really what I'm excited about.
Okay, yeah, thank you so much. Well, we have another audience raise a hand. Elijah Bernard. So can you please unmute yourself? Yeah, Bernard. Can you please unmute yourself and ask a question? Oh, okay. He put down, the audience put down the hand. Okay. Yeah. So probably, yeah. Let me ask you the last question. So what's the most popular starting points for the method development by using this new column?
Yeah, I mean, you know, so I was trained in chromatography by a guy that liked to screen phase chemistries, and you know, with they obviously in pharma the budgets can be a little bit bigger than, you know, mid-size or small-size pharma, or even the folks that are in the pharma support, you know, team. So you know, we always promote screening and trying to screen multiple modes of interaction at the same time. So you know, from a hit perspective, we would say that you would either start with the C12 or C18AR as your hydrophobic phase, and then the diphenyl, because it just gives different selectivity, different modes of interaction, and then the C18PFP as sort of the first pass in a screening portfolio. Then I would look at, you know, in step two, you would either have that C12 or C18AR, and then you would look at the aqua and RP18 amide. Those would give you a wide array of, because we've done some work in principal components analysis workup, and to look at where those probes sort of sit in that 6-dimensional space, so that you get a full view of the selectivity space, and that gives you the widest chance of taking the next best column to further method development. So you would pick probably a 3 millimeter, you know, to save solvent, or 2.1 if you have LCMS capabilities. And obviously if you had MS, that gives you the full range, where you're not only just working on retention times and UV spectra, but also seeing data. So that's sort of what we would suggest, unless we knew something specific about the analyte. Like if we knew it was, you know, some specific chemical entity, and we had some familiarity with it, we might point you in a different direction. But not knowing anything about your sample, that would be the best way to go forward.
Okay, great. Yeah, thank you so much. Yeah. So now let's move on to our next session. So then we are going to have pool questions. So then here, totally we have 2 pool questions. So I'm going to share the first pool question with you. So yeah, please put your selections on the pool questions. Yeah, this is like a little survey. So can you see the pool questions from your screen?
Yeah, you see
Yes.
that
Okay.
the poll results. It's not
Mhm.
the.
Yeah.
Can you
Okay.
go back to
The poll question.
the?
Yeah. Yeah. I didn't see the result coming in. Okay. Oops. Here. Okay. So let me try again.
I'm wondering if you need to change back to the presenter to you as the presenter.
Okay. So now let me try another one. Okay. So can you see the?
Yeah, no, it's good.
Can you see the different? Okay. Okay. That's good. Okay, I'm going to close this question. Yeah, in 5 seconds. Okay, sounds good. Yeah, so for the first question, I'm going to copy down the question in the chat box, and then you can just reply in the chat box, yes or no. Yeah, so the question is, before today, were you aware of MacMod Analytical? So this is a question, and then you can just type in your answers in the chat box, yes or no. Yeah. So are you aware of MacMod Analytical before today's webinar?
Yes, but I don't have the chat box. I'm using my cell phone. Yeah, sorry, I have the word to tell you.
Okay, thank you. Yeah. So that count as a yes. Okay, yeah, pretty good. So now we have answers keep coming in. Yeah, are you aware of MacMod before?
Yes.
Yeah, I already count you, Harry. Okay, yeah, very good. So I think I can close this this question as well. Okay, yeah, basically that concluded today's webinar. So as what I mentioned before, we have the second part. So that is mainly focuses on applications of this wonderful new technology, new column technology. So that will be on February 5th. So then I'm very looking forward to see you again on February 5th. And also, I'm also looking forward to see you on PeterCon in Boston this year, in the March. Okay, thank you again, Jeff, for sharing us with this wonderful new technology. And also thank you everyone for attending today's webinar.
Thank you, guys.
Okay, thank you.
Thank you.
Thank you. Okay, bye.
Bye.